Real quick before we start the show, it is that time again. We're going to be doing our 2021 Amp Hour listener survey. We love to hear from you, hear what you think, hear what you want to hear more of in the show, and any other feedback you might have. Our giveaway this time is going to be a copy of our guest book, Joel Dunsmore. He created the front end of the 8753, that's the VNA I've been talking about on the show here, and he has a book called The Handbook of Microwave Component Measurement that he also discusses on the show. It's the second edition. So fill out the survey, be sure to include your email address if you're interested in winning. We will ship anywhere in the world. Thanks for a lot, and we are looking forward to seeing your feedback. This is the Amp Hour Podcast. Release March 7th, 2021. Episode 533. Microwave Measurements with Joel Dunsmore. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Joel Dunsmore from Keysight Technologies.
Hi, Joel. How are you?
Doing really well.
I always have these interesting feelings when people come on the show where I've read their books before, and your book is one of the subcategories where I'm not sure I understood everything. It's like so high. It's such a in-depth topic that I'm not sure I understood everything. But I'm really glad you're here. We can start to clarify some of these things. So thanks for being on the show.
Happy to bring clarity anywhere you're clouded.
Great. Well, actually, one of the things that I'm a little clouded on is actually it's actually something you designed as well. So you are one of the main engineers on the HP 8753, which is the VNA that I have. I have the D version, but your hands are all over that machine, huh?
Yeah, I started in 1981 designing the input buffer amp as a college intern project on the receivers.
Awesome.
And by the time you got to the 8753D, every one of the RF circuits is my design.
Wow, that's awesome. Well, I have to say it is a great machine. One thing that we had talked about a little bit is that the APC7 connectors that's like one way that you can tell that it's your designs.
Yes, that's exactly right.
What is the reason for the APC7 connector? Because I think I mentioned that on the show, but maybe not the reason why it's a good fit.
Well, it's not a good fit. It's a horrible connector to use for anything practical, but it has the advantage of being the world's best connector for connector repeatability. And you have to remember the 8753 was designed before we had error correction or even computers. It's one of the first pieces of hardware that had a built-in microprocessor.
Oh, really? Oh, okay.
Yeah. The HP 8510 shipped about 9 months before, but that was like a collection of instruments. This was the first single box network analyzer. And it has basically a washing machine controller. And it was a 4 megahertz clock rate controller. And a lot of the stuff you see in the firmware is related to that. The APC7 connector was used before we had error correction. So the 8753 was designed originally, and this drove me crazy as a designer, was originally designed to not use error correction at all. To get a really good spec, the repeatability of the connector will make a difference and how well you can, how stable it is. So that APC7 is a bit more stable than Type N, and we could make our directivity spec maybe 3-4 dB better by using that connector.
Okay, so on a different machine that has a Type N connector on it, what would the error correction actually be doing in that case?
Well, it would be measuring when you connect a load to the machine, the load can't connect directly if it has a gendered connector because the pin will go into the socket and have a little bit of a gap. And that little bit of a gap, we measure its response, which is going to look like a little inductance, and we essentially subtract that out with the error correction. With the APC7, if you look at the collet, it's got like a tiny little spring in there. So it's a mating connection that has 0 offsets. So the shorts are true shorts. The opens are pretty close to opens. And the load has got no little inconsistency in it. So if you didn't use error correction, that would be important. But everybody uses error correction. So we could have changed, but we never did.
Got it. Okay. Yeah, and I mean, they make converters and other ways to do that. So at that point, I feel like it's kind of you start to get into that ecosystem of just using converters, understanding that they're there, and calibrating once they're on there. Maybe we could take a step back. Could you give us a broad definition of what a VNA is? I've always tried to give that definition on the show and why it's necessary and what people are using it for, but I feel like, having an inventor of, or, a creator of one on the show is probably the best person to hear it from.
Sure. So network analyzers are not for internets, and maybe a better word for them would be component analyzers now. They're to characterize electrical circuits. And so the things you want to characterize on an electrical circuit is the gain, which is how much signal comes out compared to how much goes in. And if you've worked with antennas before, you also want to know things like the impedance. And the impedance tends to be a complex number. So a vector network analyzer gives you a vector number, which is a magnitude and a phase, and that's a complex number. So it allows you to measure networks that have complex impedances. And anything except a DC network has a complex impedance. So if you have some inductance, you get some phase angle change on your measurements. And instead of using an oscilloscope where you can measure the sine waves on the oscilloscope, but it's hard to pick off the magnitude and phase on an oscilloscope, a vector network analyzer gives you that directly.
Yeah, that's great. That's a great explanation. I do feel like like kind of what you were talking about with the connectors as well. Everything having an impact on a measurement, like you were mentioning, the physical characteristic. That was a big shift for me. Is just so my friend Jeff, who's been on the show a lot, he kind of walked me through and talked me through a lot of this. But it's just like everything has an impact on that complex impedance that's going to be what you're trying to measure normally. And I didn't quite understand like how much that feeds back into systems and really can impact things. But that's really where the VNA starts to have a lot of import and a lot of, you're making an antenna. You want to know everything about that antenna. You probably are measuring it with the VNA.
Yes, for sure you are, as far as looking at the input match and trying to understand how can I match it to get most of the power to go into the antenna. And you need to know not only what impedance you have, am I 50 ohms or 40 ohms, but you need to know the phase angle as well. Because if you get on the wrong side of the phase angle, you can make things much worse instead of better. In fact, in the 8753, I designed the amplifier that's in the source. It has 4 stages, but the first 2 are almost identical. And I measured them stage by stage like he did before. And each one had a 2-to-1 mismatch. I said, well, that's pretty good. I should be able to put them together. I'll only get a dB of variation. But it turned out they were exactly opposite. I had 6 dB variation in the gain across the sweep. And that's what learned me up about impedance mismatch.
Right. Couple late nights in the lab will really hammer that point home, huh?
Yeah, and throwing one design away and starting a new one.
Yeah. And the subsequent conversation with the boss about that, I'm sure.
Yes, well, those things happened back in the day. You always did the cut and try. That was right at the dawn of doing computer-aided design. And so I was one of the first engineers in HP that actually used computer-aided design, and I evaluated
interesting.
every version of the ADS simulator from the very first prototype that was done by an engineer that sat just down the row from me to the final version of ADS you have today.
Wow, that's a lot of ADS, and I'm guessing you get the benefit of not having to pay the royalty or the license fee each time as well.
Yes, although I used to be able to get a permanent version, and now they say now you can only get the 18-month subscription. So I have to help out with that.
Well, I guess you still get the you're probably good for the re-up after 18 months.
Generally, they do re-up.
Yeah. That's great. And back then, so what was the time frame of that? You said you started in 81. When were you? What was the first version of ADS that you were using for development?
Oh God, I guess that would be about 84 or 85 is when it was called the Microwave Linear Simulator, MLS.
Okay.
Then that became the Microwave Nonlinear Simulator. My second boss, the guy's name is Dave Sherritt, smartest guy I personally know. I mean, we hear about guys like Einstein, but this guy could do Fourier transforms in his head. And in fact, he wrote the time domain transform code that we use in all our analyzers today. But he got tired of working on network analyzers, and so he created the nonlinear simulator and harmonic balance simulations. So since I work for him, he often had me evaluate this stuff. So I got as
Right.
part of my
Right.
job, besides being a designer, I got to evaluate some of his work.
That's really cool. Yeah, and I'm sure you've seen the all colors of the levels of development and all the warts that are underneath the hood. I'm guessing too, huh?
There are a lot of warts underneath that hood.
Yeah, yeah, yeah. Nonlinear calculations are. Are there magic numbers in there as well? Like, well, it usually does this, and you just put in a 1.7 factor here. I just always assume there's something like that underneath.
There are some things in some of the transformations we did to make them match up with the older equipment.
Yeah.
And sometimes we have to, even in our instruments, sometimes we do some things that you say, that doesn't make sense to do it, but you need to do it in order to have the same answers that you used to get with the analog equipment.
Yeah.
We get that in the spectrum analyzers, for example.
Oh, yeah. Okay.
There's a thing called DANL, displayed average noise level. And it used to be that the logging circuit that changed the voltage to dBs happened before the display. And so if you did it that way, you get a 1 dB lower reading than if you average the power first. And averaging the power first is the right way to do it.
Mm-hmm.
But nobody wanted to take a 1 dB hit on their spec. So all the instrumentation manufacturers define DANL as log first, then average.
It's art imitating life, imitating art, kind of one of those things.
Roughly speaking.
Yeah, that's great. Oh wow. Yeah, and I mean that's amazing because that shows like how much, especially in the test equipment industry too. Like spec is just like everything. It's that spec sheet that's going to drive how much time you spend on the next feature and like how many times you test something. And it's just it's a crazy game to play in.
And what you do in terms of measuring and correcting. One of the things that's happened in modern equipment is we do much more corrections in our instruments now than we ever did before.
What do you mean by that?
So, well, of course, we measure the frequency response and we correct the frequency response, but now we're doing nonlinear corrections in our instruments. So we're trying to measure
Okay.
the nonlinear characteristics. We build nonlinear models.
Uh-huh.
One of the guy that sits across the way from me, a guy named David Root, invented something called X parameters that are used for nonlinear modeling. So we use that applied to our instrumentation so that we can drive the sources and receivers harder than you normally would and still get a good result.
Okay. Yeah, and that makes sense. And that probably is that because you're dealing with kind of the perfect nature of a model kind of hitting the real world. Is that kind of the I call it fudge factor normally, but I don't think people like to call it that.
Well, it's not exactly a fudge factor, but if you're driving an amplifier into compression, so it's going to clip the
Yeah.
top of the waveform.
Right.
If you have the circuits that can drive the peaks of the waveform a little harder, so when the amplifier clips it, they show up to be the right level, then that's how you can restore linearity.
Got it. Yeah, and yeah, if it's repeatable, if you can prove it's repeatable too, it's like then what's the problem there? I would imagine that's.
And of course we have to characterize it over temperature when it's not repeatable, so we can know okay, at this temperature we should use this factor.
Yeah. Well, speaking of corrections, let's talk a little bit about calibration because that's another thing that as I got started with my VNA, I ran smack into a lot of strife. What is a calibration on a VNA and like what is it necessary for and how do people get it wrong?
So calibration is basically you measure something that you know its true value, and then you just correct the readings to get the true value. And for vector analyzers, to do impedance, you need to have 3 true things. So we usually use an open, a short, and a load. And the biggest mistake that we made as an instrumentation manufacturer is calling them an open, a short, and a load. If we would have only called them an offset open and an offset short back in 1972 or whenever it was first invented, we would save so much grief from people saying, I put my short on and it's not a dot. Why is it not a dot? All of our opens and shorts are offset, so they all have a little arc.
That's like a physical characteristic, you mean, is an arc?
Right.
Or the arc is the thing that shows up on the VNA.
The arc is the thing that shows up on the VNA. They show up as if you look at the phase of a short is not 180 degrees. It starts at 180 degrees and it goes to, swings around 15 or 20 degrees more. The opens are even more problem because the open circuit actually is a capacitor. If you think about it, you cut the end off of a piece of coax, it's got something we call fringing capacitance, and that adds an extra amount of phase. So when people look at the phase of an open, they expect it to be 0 degrees, but it's 15, 20 degrees as they go up in frequency, and they yell at us, how come it's not the right answer? I had a professor that insisted an open had to be an open, and how could it have any phase? Sometimes you just tell them how to fix it. You say, oh, well, you can make this adjustment and it'll turn it to 0. It won't be the right answer. But...
Right. It'll look as it appears in your head, huh?
Exactly.
Interesting. And so people are using this. So basically, this is to get rid of stuff that's internally happening in the VNA. Is that right? Mostly
it's to get rid of stuff that happens between the VNA connection and the thing you're trying to measure. So you got your PC board with your little RF amplifier you want to test, and you want to know the input impedance of that RF amplifier. You're going to connect it to the VNA through a test port cable. And cables are horrible. Cables, I say in my book, cables are like dogs. Either they are bad, they've been bad, or they're going to be bad. And if they happen to be good, they only stay good with great care. So you have to be really careful with cables. You put a bend in them, it changes their impedance. And that's usually what we're calibrating out.
Yeah, and I guess one of the things that I learned later on, for some reason it just never really stuck until I was doing cable stuff too. It's just like the idea of just a coaxial cable, and that there's an insulation between where the cable is and then the ground around the cable. Like, it's just this consistent amount of stuff between the conductor and the ground all the way through. And like, for some reason that never really sunk in. So then when I was bending stuff around, it's like, of course you're putting stresses on these things. There's there's like an effect too, like not pyroelectric, but what is from like actually like flexing a cable as well, that actually impacts how the signal response is throughout these cables.
Well, one of the things that happens when you flex the cable, you squeeze that dielectric. That's what we call that insulator in behind, dielectric. And the dielectric constant is the ratio of the E field to the H field in the cable, roughly speaking. And so as you squeeze it, you can change this dielectric constant a little bit. But also, when you bend the cable, the outer conductor kind of pushes up, the dielectric pushes down. And so you're actually changing the inside dimensions of that cable. And the impedance of a cable is directly related to its dimensions. So that's usually what you're doing when you bend a cable, is you're physically changing its impedance. Now, if you look at what's called mainline cable that the cable TV guys use, and I worked with a lot of cable TV guys. I've been to their factories where they have a tunnel that's a mile long, and they send an extruded piece of metal down a mile to another building a mile away. Then they draw the dielectric through by having, call it a mouse, but they basically tie the dielectric, which is plastic, to essentially like a little cannonball, and they shoot it down a mile with compressed air, and it pops out the other end, and they drag the dielectric through, and then they do the same thing with the center conductor. And they pull this whole thing through a kind of a fixture that compresses the outer conductor to the center conductor, and they wind it around big reels. And you've seen those big reels on the back of the cable TV trucks.
Yeah.
So this is all done in the South, in Carolina and Tennessee, where they got lots of cockroaches. So a cockroach lands on that big pulley where they're wheeling it around, and it puts a little ping, a little dent in the outer conductor. And they can tell by looking at the impedance versus frequency. They'll get a little spike at one frequency, and they'll say, oh yeah, we got a problem with the pulley number 17, because that's the size of the pulley. So those are the kinds of things you have to deal with, impedance mismatch.
Right. And so in those cases, I mean, well, obviously that's like a high power, high accuracy kind of thing as well. I mean, would someone like...
It's super low loss.
Yeah. Would someone like that then go and remake the cable in that case? Or would they just kind of, would they be able to correct for that?
Depends on how bad it is. Sometimes they can find out where it is and just cut that bad piece out. But if it's one of these things that happens every 1 meter for 1,000 meters, they throw that away.
Got it. Yeah. I mean, right.
These cables are something like, a dB per 100 meters of loss. So a 1,000-meter cable will only have 10 dB of loss. The cables you buy or that you have at your lab are probably a dB in 1 meter, so they're 100 times more lossy.
Just because of the cost and the process control, that kind of thing.
Yeah, and it's basically the inside material because these things are sometimes they're even silver coated on the inside to get the best conductivity.
Mm.
Power loss is a big thing in that world. Also in the SATCOM world, they want to have super low power loss. So remember you talking about filters on your show and the comb line filters you saw in your transponder. Those things are all silver coated on the inside.
Yeah, that was Dave talking about the airplane transponder. I think he had cracked one open.
Yep.
Yeah.
And they do look like magic. I remember him saying something about having it just the center conductor goes to ground inside. So how does the thing work?
Yeah. How does that thing, Joel? How does that work?
It's all about length. The
Okay.
what happens is that center conductor goes is just a wire passing through. Probably they have a little piece of Teflon, so it's like a wire that passes through the body and then shorts to the ground inside. But that length of line that it's shorting to is exactly the right length to form essentially a shorted half wave antenna. So it's a probe essentially. It's a little
Oh,
antenna that's going to generate. Because how does an antenna work? I mean, it's just a wire that's open at the end, but if it's the right
right.
length,
Yeah.
you can stand
Yeah.
a wave on it. And so
Hmm.
that's generating a little electromagnetic field. And each one of those combs in there is a little resonator that's just coupled to that magnetic field and coupled to each other. So that's how it works.
Hmm.
It's all length. That's really the difference between low frequency and RF is the length means everything in RF.
Yeah. 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 And I mean, again, it comes back to that physical. I mean, you mentioned the cables already, and we talked about the connectors and now the comb line filters and everything. It is just crazy to me that like how much the mechanical aspect and well, the length like you're talking about, like how much that impacts things. I mean, it really is just the natural phenomena of resonances that ends up creating all these interactions that I don't I guess I still don't have an intuitive feel for it. How does one gather that intuitive feel?
Well, if you do any radio work, you kind of get a sense by the size of the antenna that you're using. So if you look at a cell phone, or the old, Ericsson cell phones had that little pull-out antenna. So that was a wavelength long quarter
Hmm.
wave antenna. So anything that's a big fraction of that is going to affect the signal.
Hmm.
You can kind of have an idea as you go. 5G is the new thing, and it happens at a much higher frequency, 10 times the frequency of cellular.
Hmm.
So for a 5G system, something that's only 1 or 2 centimeters long will have a huge impact on the signal. Ham radio, I was a ham radio operator for years. So if you have an 80-meter system,
Yeah.
your wavelength's 80 meters, what's a meter here or there? It's not going to matter by a few degrees.
That's right. That's right. When you're throwing your antenna up over a tree, you're probably not dealing in centimeters.
Exactly so. The cell bands are what we used to call microwave bands back in the day, but now
Hmm.
that's just considered run-of-the-mill RF.
Yeah, yeah. Where do you put the line for microwave these days?
Uh, well, it's very clear. The line is exactly 6 gigahertz, the maximum frequency of the 8753. That's the definition of RF is what the 8753 can cover.
Got it. Got it. Past that, and well, it does seem like past that, and the price goes up for sure. So that seems consistent at least.
Also true.
Yeah. I mean, the cables especially again back to the physical side of thing. I remember Shariar from the Signal Path. He shows some things where he's just like I think he was at a trade show and he was just like fawning over these cables. And then I was like, oh, they must be great cables. I went and looked them up and I'm like, oh yeah, wow, the price shows that those are great cables. Like it's crazy how much that stuff matters.
I mean, it's not unusual to pay $1,000 for a microwave
Yeah.
cable.
Yeah.
And they're good until you hang something off of, you connect your cable to your instrument, you connect it to something, it bends over the edge of a cable and puts a little ding in the cable, and now that $1,000 cable is no good anymore.
It's great to tie your shoes with though. Then I mean, you could do a lot of you could give it to your cat if you want to. Like there's just really a lot of other things there.
My boss actually took a picture of a couple of guys at one of our customers taking a network analyzer out of the trunk of their car by pulling it out by the cables and holding it by the cables.
Oh, ouch.
Those are easily $1,000 each cables, and I don't think they would be good anymore.
Why were the cables even plugged in when they were moving it? That's another crazy thing. Like, it just seems like you're gonna start knocking things sideways.
They were movers, they're movers. They're not engineers. So they were told, here's a piece of equipment. It has to move. And the cables were cooked at the time. So they just said, well, this will be an
Yeah.
easy way to pick it up. We'll just pick it up by these. That's horrible.
Wow. Wow. Well, so you mentioned the 6 gigahertz limit on the 8753. I mean, obviously, time marches on, technology marches on, and it is not 6 gigahertz limits anymore. I mean, this 8753 is still. But what is the upper end of VNAs these days? Like, what is the high end that people use?
If you're talking about a single box instrument, we make something up to 70, and we can even extend it to 72 gigahertz for a single box instrument. Once you get above the 70 gigahertz range, then we start to make what we call millimeter heads. They're millimeter because that's the millimeter waves. Anything above 30 gigahertz is considered a millimeter wave. But in the bands of 70 to 120 gigahertz, we make these little heads that go on the network analyzer. And you almost have to do that anyhow, because at those frequencies, the loss is so great. If you put a 1 meter cable on at 100 gigahertz, you wouldn't have any signal left coming out of it.
Mm-hmm. Yeah. So yeah, that's and like, what are the? I mean, so you mentioned 5G, and it seems like there's some frequencies up there. Who else are using these kind of 100 gigahertz type of VNAs?
Well, of course, there's 6G that's supposed to go up to 300 gigahertz, and we're starting to do a lot of work on that.
Oh wow.
SATCOM uses that for satellite to satellite communications. It uses the higher frequencies because the atmospheric absorption protects those signals from being intercepted.
Yeah. Just because of like where water resonates and stuff like that.
Exactly. It's actually water absorption and other oxygen absorption that will absorb those signals. That's why most satellite communications is actually below 50 gigahertz, because that's where the absorption function starts to increase. Although they're pushing that up now. I just heard a SATCOM band goes up to 53 gigahertz. So our newest network analyzers, instead of stopping at 50 gigahertz, we pushed them up to 53 gigahertz for just that reason. So you can get a handheld, we call it a Streamline, but it's a handheld USB powered network analyzer to 53 gigahertz now.
sounds affordable.
It's probably not that much more expensive than your 8753D was when it was brand new.
That's true. Mine was made in '96. You'd ask me this by email, and I don't know the serial number offhand, but I know when the screen pops up, it says '96. So
okay, so is that older than you or younger than you?
That is about 10 to 15 years older than me. So yeah, I was definitely a middle schooler when this thing was. I was not thinking about signals when this thing came to life.
Yeah.
I think I maybe got my first walkie-talkies around that time. So
perfect.
Yeah. About my interest in RF peaked. It started, I guess, not peaked. Started then. Okay, so the 53 gigahertz and that realm of things. I mean, can you give us a relative measure as well? I mean, like what is the expected losses? Say like a satellite to satellite. It's there's not much. There's no atmosphere up there, but like even over that distance, how much loss do you expect when you're doing a satellite to satellite communication link using that? Do you expect like 100 dB losses, or what do you expect there?
It all comes to the beam shape, right? If you have an anisotropic, well, of course, in space, there's no losses, just, steradians is what they're called, 4 pi r squared, the signal goes out. There's not much loss in space at all, so it just radiates uniformly. And then you will beamform that. All these satellites have big beamformers. If you've seen the Starlink teardown, that has that big pizza box with 1,000 elements. I saw that a few years probably before you did, but those are, each one of those elements is kind of aligned to point in one direction. And if you can so it all comes down to how narrow you can make your beam, sets how much loss you have.
Got it. So it's like the expanding cone of diffusion of signal or that kind of thing.
Exactly.
You make the cone narrower.
Just like shining your flashlight at night is very bright. When you shine it on the ground close to you, you try and spotlight the deer.
Right.
It gets pretty diffuse.
Right. But if you can get a laser pointer, you get a much better shot at pinpointing something.
Collimated beams, they make a difference.
Got it. Okay. Yeah, that's interesting. So then, okay, so say it is a beam instead, beam formed. What are relative losses then? I mean, again, I just don't really have a good intuitive feel for any of this stuff.
So I'm working on a little phased array antenna test methodology right now, and I have a 64 element phased array antenna that I got from a fellow named Professor Rabiz at University of San Diego. He's one of the leading lights of phased array stuff. I've been working with him to do some testing. I have a what's called a horn antenna, which has about 24 dB a gain. I have this phased array antenna, and the loss between them 1 meter apart at 39 gigahertz is about 25 dB. So that's 1 meter.
Okay. Okay. So a little bit more for satellites that are flying around the Earth.
So if you're going to have 100 kilometers, you got to have a lot more elements to make that beam a lot more tight,
Yeah.
so you can
Yeah.
get what we call antenna gain.
Yeah.
That's why 5G, you'll always hear people talk about 5G with MIMO, but also with what they call phased array or beam steering,
Hmm.
because there's just too much loss. You can't afford to transmit energy omnidirectionally. You have to focus the energy on the user. So these 5G applications, they actually have to know where you are and point that beam to you and track you out.
Yep. Yeah, and it seems. I mean, I know it's possible. Obviously, I've seen a lot of phased array things out there, but it still is crazy to me thinking about like it. I guess it happens even with 4G towers that there's some amount of beam forming, but like it's still like my brain boggles when I think about that. Like, oh, they're just pointing a beam at me from wherever.
Yeah, I think the 4G, they have maybe 6 beams per sector, something like that. And these 5G stuff are going to have hundreds of beams per sector. So that's the thing
wow.
that really boggles my mind, is the
Yeah.
digital processing behind that to take all these signals and know who needs to be separated and who needs to be pointed which direction, and then put it all together so when the antenna is hit with a signal, it points out 17 different beams in 13 different directions.
Yeah. And all that just so people can, watch a YouTube video.
Watch YouTube
That's
video while they're driving. That's the
that's
important
right.
part.
Yeah, exactly. Yeah, I mean that is kind of it bugs me sometimes thinking about that. Usually the one that my brain switches to is just like all this advanced technology, and it's just people on Tinder swiping right and left, and it's just like, oh man, like.
I wouldn't know about that.
Well, I mean, just yeah, just broadly as like a that's what the human race comes down to, is just serving commercial needs that are the same commercial needs that we've had for millennia.
All right, so you have your finger on the pulse of the nation. Which uses more bits, cat videos or Tinder?
Oh, cat videos for sure. Yeah,
Yeah.
yeah. I mean, just because it's video, multiple frames. So, yeah.
And especially if you're a picture of a lawyer turning into a cat, I don't know
Oh
if you've
yeah,
heard
that
about
I
that.
mean, yeah. So that just happened here. That was a great video. I'm sure people have seen that, but if they haven't, look up cat Zoom call or something. Oh my god, best video 2021 so far. So these are obviously tools that people are using to measure things like satellites and similar. I mean, let's get back to the device itself, the VNA. I
Yep.
mean, what happens on the other side of that connector, right? So we've got the APC7, or we've got whatever the new type of connector is on there. What is behind that? What is inside the box?
So it's inside the box. The first thing is the signal source. You have to create a signal. Usually it's a CW signal, but the modern ones can do other things. You create essentially a sine wave signal. CW means continuous wave, but in fact, it's not continuous. We sweep it in frequency, we sweep it in power. And usually on these networks, you want to measure its characteristics as it changes frequency. Biggest things they're used for is like testing filters and making sure the filter is rejecting where it's supposed to reject and passing signals where it's supposed to
Yeah.
pass a signal. And that signal source then goes to what we call a signal separator or a reflectometer. And because of the way RF signals work, you can't really have an open or a short. So you can't do the traditional electrical engineering of, what's the short circuit measurements or open circuit measurements. You have to
Hmm.
do it in what's called a constant impedance environment. So we use something called a directional coupler that can measure how the signal is coming out of the source, and a second directional coupler that can measure how much signal is reflecting from the device that we're trying to measure. And by taking that ratio of the signal that comes out of the source and the signal that comes back from your device, that ratio tells us the impedance. So the basic network analyzer is a signal generator, dual coupler or reflectometer. And then on either side of those couplers, you have to have a receiver. And the receiver has to be coherent so that when it sees a signal, the two receivers, one for the reference or the signal source and one for the test signal, it can compare the amplitude and phase. So a signal source, directional coupler, and a vector receiver are the three big pieces.
Yeah, that's a very succinct definition of it. I like that. I mean, I compare that again to, Shariar is my video reference for all these things too, the signal path, and it's just like, he opens up a box and I'm just like, oh, he's able to call out the different sections within that. He's obviously seen a lot. I'm sure, I know you have seen a lot as well. But again, it's just like it looks like a treasure map to me when you look at like a circuit board on a modern VNA. It's just crazy.
Oh, and the things, so that sounds really simple, but the things you have to do in order to get the power to be super flat, people want a tenth of a
Right.
dB precision across 0 to 70 gigahertz. They want the signals to be clean. So in our high performance VNA, we call it the PNA, we have 33 bands of switch filters to clean up the signal.
Oh, wow. Okay.
And that's a microcircuit. It's a gold brick, essentially, let's say 6 inches wide and a foot long with 82 DC feeds to control all that stuff. That's the most
Wow.
expensive single circuit we built in Keysight.
Wow. That's and so the filters then are basically it's because of how a signal coming back through at like 36 gigahertz or some random frequency might resonate with other things within the circuit. Is that the thought, or why are there so many filters in there?
So our customers want us to put out a signal that's got no other signals associated. If we put out a 10 gigahertz signal, it can't have a 30 gigahertz harmonic or a 20
Mm,
gigahertz second harmonic. It can't have spurs. And the reason they don't want those is because they want to make sure that what they're measuring is coming from their device only and not coming from the
mm-hmm,
test equipment.
mm.
And so trying to make such a clean signal just coming out of an oscillator is really difficult. And people want like one part in a million in terms of error signals. So we have to go to a lot of effort to get those things cleaned up.
Got it. Okay, so as it's sweeping through different frequencies, a new spurious signal might pop up during the generation of that. Is that part of why the filtering happens?
Exactly.
Okay.
The oscillator might generate it. And also, sometimes our oscillators are banded. So maybe it goes from 2 to 4 gigahertz, and then we have to go through a times 2 multiplier to get 4 to 8
Mm,
gigahertz and through another multiplier. And each of
mm-hmm.
those multipliers generates their sets of harmonics. So we have to clean all that stuff up. The reason they want it clean is because if you have a cell phone receiver, let's say, it's got a specification that says, I need to be able to receive a really weak signal in the presence of a strong signal. So they need to provide, while they're testing these things, exactly precise signals. And if those levels are off at all,
Mm.
their unit won't pass their production tests, and we'll hear about it.
Right, that's right. Yeah, well, I think that's again like all the complexity that you've explained so far. I mean, it also just points right back to the fact that it's very difficult to make this stuff in the first place, and even more difficult to make it cost effectively. I mean, it is cost effective as it is. I just imagine from the scale required, and yeah, it sounds like a really tough problem to solve.
It really does come down to scale, and you'd be surprised if you go, to the overseas manufacturers. If we can improve something a little bit, they will pay for that. You think nobody's going to pay a lot of money in manufacturing for this equipment, but if they can speed a test up because they don't have to dodge
Yeah,
a signal that's a bad signal, that is all real money to them, and they know the cost of tests down to the cost per microsecond.
got it. So you're saying like handset manufacturers, similar kind of things there.
Yeah, and go one step below that, the component manufacturers. So you
Yeah.
talked about, I know on an earlier show, a regulator for a penny
Mm-hmm.
and capacitors that cost less than a penny.
Mm-hmm.
And those all have to be tested. And so if you're doing a million capacitors,
Right. Times however many billions are made a day, and on and on and on.
yeah, I think it is billions a day too.
Yeah. Oh yeah. Yeah. Well, that's great. And I mean, yeah, I mean the process efficiency type stuff too. It's just like the combination of expensive machine that needs to go and test many different things. Yeah, It's quite an equation, like you said, and quite an equation to solve.
And that's one of the things that's changed in the world of network analyzers. It used to be you'd build a test system with a switch in a spectrum analyzer, you switch in a signal generator, maybe switch in a noise figure meter to
Hmm.
do your testing. Nobody wants to do that. They want one piece of equipment that can test everything at the same time.
Got it. Got it. So then, do they? Is it like the VNA or the network analyzer is plugging into like a test head or something like that, so that it can switch to all these things?
It's exactly like a test head. If you've ever seen
Okay.
a wafer prober probing a digital
Yeah.
wafer, the RF
Hmm.
wafer probers look the same, except they have some RF cables that go onto them.
Mm.
And they touch down on their device and they want to measure everything and they want to measure it all in zero time.
Right. Yeah. Yeah. I mean, so you mentioned spectrum analyzer. So then how is a spectrum analyzer different than from a network analyzer?
So the principal difference, of course, is it doesn't have a source because it's only measuring signals.
Hmm.
The spectrum analyzers traditionally would have some kind of a hardware swept filter that would sweep across the spectrum and remove signals from the detector. So it's essentially a sweeping filter with a detector. But some of the modern measurements the filters can't sweep fast enough or can't be wide enough. So they have removed that filter and use digital techniques. And that's what we do in the PNA, which has our network analyzer, the vector network analyzer with the built-in spectrum analyzer option, essentially uses a digital filter, a complicated digital filter with a complicated algorithm to pick out what's the true signals from the signal that we're measuring. So a network analyzer really has the same hardware as a spectrum analyzer, plus a source and a reflectometer.
Right. Right. You have to be able to switch that source in. And I think Alan Wolke, who we've had on the show before, I think he showed on YouTube. Again, my YouTube is my reference for a lot of this stuff, but he
Sure.
showed actually how to do this stuff with, I think, a cheaper scope and a signal generator, just like the basics of it. And it was great to see, like, to understand how signals have to switch in, how you have to sweep across frequencies and all that stuff. And it's very non-trivial in order to get a signal injected into a circuit you're also trying to measure at the same time.
Yeah. Part of the problem is you have to, and this is actually where the RF is different than a lot of other things, is in the RF, we define the input and output to be this 50 ohm impedance. Typically, it's 50 ohms. So the test equipment, if it has that same impedance, it doesn't affect the behavior. Whereas if you've ever put an oscilloscope on a circuit and the circuit works when the oscilloscope is connected and you disconnect it and it doesn't work, that's
Yeah.
because the impedance loading is maybe stopping that amplifier of yours from oscillating.
Mm. Yeah, and that I test equipment impacting circuits is is a pastime of mine,
Yes,
and also
everybody.
hair tearing. I think that's also usually goes along with
Yeah.
that. So yeah, that's great. So you mentioned like how things impact things, but what about like how noise impacts it then as well?
So we have kind of two aspects of noise that we usually deal with. One aspect is we call it Ktb noise or Boltzmann constant noise. It's just everything is warm. So if something is warm, it produces a voltage and a noise voltage. And our receivers produce their own noise. We try to make them as low as we can, but they do produce noise. The circuits produce noise. And we measure that with something called noise figure. So it's a way of evaluating things like amplifiers and receivers. And you say the lower the noise figure, you'd like it to be 0 dB. But even a 0 dB receiver doesn't have zero noise. It just has the noise of a thermal noise. And that still impacts the how well you can receive something. So what do they do when they want really low noise?
Make it cold.
Make it really cold. And I've been
Yeah.
working with different groups at different universities that are trying to do millikelvin temperature network analysis, and that's just
Wow.
a whole nother challenge where it might take you a day to connect your open. You connect your open, you bring the cryostat down to cold
uh,
temperature. It takes 8 hours. You measure it. That's
to be
that's
the nitrogen or helium vendor to those folks. Just
that's
make money hand over fist.
horrible. It's horrible.
Yeah.
That's not a job I would enjoy. You have to have a different kind of patience to do that.
Yeah. Yeah. Millikelvin. Yeah, that's crazy.
And then the other noise we deal with is something called phase noise, or you might call it jitter in a digital circuit. And it's the fact that things happen at times that you don't think they're supposed to happen. So you're generating a clock signal to drive your digital circuit, and you think it's 10 megahertz, but sometimes it's 9.99, and sometimes it's 10.01, and it wiggles forth and back. And that can cause problems if you have high-speed circuitry or you're trying to generate signals for communications. If those clock signals wiggle back and forth too much, you lose track, and then you can't lock on your signal.
Yeah.
And that's what causes the problem when you're talking on your phone and you're driving too fast away from the cell station. It can't track you out. So the frequency shift associated with the speed is another issue, but the noise impacts that as well.
Oh, interesting. Could you talk a little bit more about that? I mean, obviously, I've experienced that, and I kind of understand it, but like, what is the physics happening there?
So there's two kinds of physics happening. One is the noise aspect, where the station has to figure out what frequency you're transmitting, because you guys don't have a common clock. You got a little crystal in your phone, it's got a crystal in the base station, and they both think they know what frequency is, but it's not the same. So part of the protocol of making the connection of the call is it says what frequency are you at and figures that out. As you drive around and as your cell phone, gets hot or cold or moves in different places, its frequency shifts a little bit. If it shifts too much, that can cause you to drop a call. But the most common thing that causes you to drop a call is what we call multipath. The signal coming to your handset's bouncing around the room, and it's adding and subtracting to itself all the time. And when you move into a spot where two signals of the same size cancel each other, all of a sudden the phone goes dead, and you're like, "What happened? I have a dead zone here."
That's the I'm walking into an elevator problem, right?
The elevator problem's slightly different.
Oh, is it? Okay.
Walking into the elevator is you're going into a Faraday cage, so you're essentially
Oh, okay.
shielding yourself.
Got it.
And you've heard of like Wi-Fi with MIMO. The whole idea of
Yep.
MIMO is you've got multiple antennas. So each antenna is receiving is physically in a different location. So it's physically receiving a slightly different version of the signal. Maybe one antenna's got the signal that's bounced off the refrigerator, and another antenna's got the signal that's bounced off the television.
Yeah.
And the hope with MIMO is at least one of those antennas is going to pick up a signal strong enough to keep the communications path open.
Right. So it's spreading the problem around, huh?
Exactly.
Yeah.
Or actually avoiding deep holes.
MIMO is multi in, multi out. What is the number of transmitter receivers that you expect on a MIMO system in 2021?
Oh, it depends. Some of these backhauls are going to big numbers, 16 up to 64, I've heard. Haven't actually seen that, but we've had people that have asked us to make 64 port network analyzers to test 64 port antennas. And I think
Wow.
those are going into MIMO systems.
Wow, that sounds like a salesperson's dream.
Those do come a bit dear.
Engineer's nightmare, of course.
Not so bad. You make a really good 2-port one, and then so we've switched to a thing called, or recently started making a lot of instruments in PXI. That's a modular instrumentation. So you make a really nice 2-port PXI analyzer, and you slot in 32 of them into a couple of chassis, and you have a 64-port network analyzer just like that.
Okay. And in that case, would you have so if it's like a 64 port MIMO thing, it would be 64 cables as well, going to 64 elements onto like a PCB antenna or something similar, or what does an antenna look like in that case?
Yeah, so these are ones I've seen are base station styles. So they're maybe 10 centimeters by 50 centimeters, something like that. And they are they'll have 64 blind mate connectors on the back of them. The instrument will sit on a rack next to the test fixture. They'll have 64 cables that go to these blind mate connectors. Then you have to do 64 sets of calibrations on the end of each of those cables. So they'll have a robot that'll hook up the open short loads to the ends of the cables, and then they snap on this antenna onto all 64 blind mate connectors and measure it all at the same time.
Wow. I would love to see that. A robot putting on putting on the calibration. That's that's crazy to me. Like the robot handling, like actually screwing on SMA or whatever the equivalent would be.
Well, it's better. I was with one customer down in the Southland in Los Angeles one of the big aerospace defense customers. They were doing a satellite system that had 30 inputs and 30 outputs, and they had a guy in there screwing on the open shorts and loads that would take him something like 2 weeks to do the full calibration, because he had something like 900 paths that we were measuring, because it's really from every port, every combination of every port to every port.
Yeah. Not to mention the carpal tunnel from just screwing things on and off so many times.
It's crazy. And so, of course, they asked us to help them out with that problem. And we developed a system that could knock that down by like a factor of 100. So they could do 30 connections instead of 900 connections.
Wow.
And
wow.
Those are the kinds of things that they'll pay you a lot of money in terms of how much your instrument costs.
Oh, totally. Yeah. Yeah, that's, process efficiency right there, right? It's just, I don't ever think about it in terms of calibration, but especially at the scale that these things are operating at. Because of the hunger for connectivity and moving bits in such crazy amounts, especially in the modern era with having so many, just how many cell towers you need out there. It's just you got to have a piece of test equipment testing everything. You can't just assume it's going to be fine. It's crazy.
And the thing that you run into is these folks, they actually want stuff to work. You say, I got a gig speed connection. They actually want to see that it's a gig speed connection. And how many times have you read, well, I have this gig speed connection, I'm getting 100 megabits per second. But, that's just what happens. I think a lot of times what occurs is just little discontinuities, little badnesses stack up so fast at these super high speeds that you can give up performance so fast. You spend a lot of money to get the high performance, and you have to spend a little bit of extra money to make sure you maintain it.
Yeah. It is very interesting too. Especially because I think, when I think about Keysight, I think about test equipment broadly, I think about on my bench, right? That's where I expect things to be. But yeah, it's the factories where this stuff, that's where the money is. That's where the rubber hits the road. It seems like
that's where all the problems are. And
well, that too, yeah.
Usually, I like to. So at my level right now, I only get involved with customers if they have $1 million problem. You got $1 million problem? I'll come in and talk to you about it.
Got it. Oh, cool. You're the fixer. Is that right?
I've been to so many places, and sometimes the fixing is surprisingly simple. I was in the Far East where they said, your systems are just not working. They're drifting terrible. And, I asked the inevitable question, have you connected the reference, the 10 megahertz reference? Yeah, absolutely we have. So we came around to software. Well, here's a software way you can track out the drift. And they said, great, that works. Next time I went to visit them, I said, let me see that system that's drifting. And they connected the reference in to the reference in, because the person who was doing the work wasn't a native English speaker. So reference, it's like A to A, B to B.
That's right.
And so that was a problem that you couldn't solve except by being there.
Well, yeah, I have to say, so as someone who has to troubleshoot people's hardware remotely, I will say the first thing I ask people to do is take a picture of it, because that is that's a very human problem, right? That's expensive. That's an expensive fix for a simple thing.
FaceTime helps out a lot in that case.
Yeah, right. Yeah, that's great.
But then just the old stupid 60, or in other countries, 50 hertz signals floating around.
Yeah.
I went to give a presentation to one of our large customers, and they said, yeah, we're not doing a presentation today. We have a problem in the lab. So they put me in a bunny suit, and I had to go up to their lab. And they're showing me, see this, one of our network analyzers has the ability to also measure DC at the same time as RF. So you want to do that for power added efficiency. And they're saying your DC trace, it's terrible. It's wiggling up and down. It's all noisy. So I'm adjusting the speed. And when I get the speed to where it can do about 200 millisecond sweeps, let's see, 10 cycles, 200 milliseconds, that's 50 hertz there. They had a giant ground loop on their test station. So they're running amps through the ground of our system. And I told them, you have a ground loop. No, there's no ground loop. So we just start disconnecting other pieces of equipment, and all of a sudden the ripple went away, and it's like, okay,
falls right into place.
I'm sure you've ran into those kinds of things.
I specifically at my days at Keithley, it was one day a firmware change had flipped a bit that was the 50, 60 hertz internal calculation thing on the ADD. It was a DC thing, so it was low and slow, but like that offset, just the 60 hertz line cycle thing. It it was like 5/6 of what it should have been. It was like, oh, okay. So yeah, that's
And how long does it take you to find that the first time?
the first time a week. The second time I thought to look. So
Yeah,
yeah.
it's not that I'm so smart. It's just I've been around long enough to see all these things.
I mean, that's the thing. It's you are the physical incarnation of that engineering cone of the guy that walks in with a piece of chalk, and it's $49,999 of knowing where to put the piece of chalk, or the mark with the piece of chalk, whatever.
Exactly.
Same old engineering story, right?
Except that everything's new again. So all of the
Right.
problems that you never thought you'd see,
Yeah.
eventually they show up, and then you're taking a week or two to figure out something that seems like it should have been simple to know.
Well, Joel, I have to say it's reassuring that someone with your level of expertise is also frustrated with that, because some days I get frustrated with like a UART. It's just like I can't
I've
get it
done
to
this
work.
before. I know
Yeah,
it should
exactly.
work.
Yeah, yeah. Well, speaking of your extensive experience, we have not even brought up the fact that you have a book that's on my bench and is my favorite of the books that I got as I was frantically trying to learn Vna Is. Let's talk a little bit about that. So I have the first edition, I think, the microwave component measurements,
Yep.
and there is a new edition.
Yeah. So the new edition, first edition was in 2012, and it was all network analyzers and CW signals, swept sine signals. And since then, we've added a lot of capabilities, not just us, all other competitors as well. So added the capabilities to do spectrum analysis, to do modulated measurements, to do complicated noise figure measurements. So I had to come up with the second edition to add all that new capability in to explain what we do and how we do it. And I go down to essentially the mathematics of what's going on inside the analyzer. So if you want to recreate the error correction we're doing, or understand why we get a power number that we get, all that math is in there, as well as a lot of very just practical examples. If you're measuring an amplifier and it's got to be 50 watts output power, how can you avoid blowing up your equipment? Here's the block diagram you use.
I appreciate that, yeah, because I'm pretty good at blowing things up, and this helped me do less of that.
Yeah, there's a whole chapter on fixturing and all the tricks of dealing with PC board fixtures, and how can you remove those effects.
Yeah. You mentioned all the things that are changing since the 2009 book came out. Why is all this stuff changing so much?
So a lot of it is just this push for the both high-speed tests, but also they want to have better accuracy in the tests. So a standalone noise figure analyzer is pretty accurate, but its largest error is caused by the impedance mismatch between its system and the thing you're measuring. Since network analyzers measure impedance mismatch, if you put a noise figure analyzer inside a network analyzer, you can remove that error. And the noise figure analyzer, 90% of it's the same hardware as a network analyzer. So you can get the noise figure analyzer capability with only a marginal increase in the material cost of the instrument.
Right,
so
right.
makes things less expensive, but more importantly, it makes them work better.
Yeah.
So I like to say our new P&A is the world's most accurate spectrum analyzer, not because it's so accurate as a spectrum analyzer, but because we can apply the vector error correction to it that if you don't have a network analyzer inside your spectrum analyzer, you can't do that.
Yeah. So it's like it's kind of like the kitchen sink type of approach to things, but because you have all these other adjustment tools that are in there in order to make a network analyzer, that's what really makes the magic happen, it seems like.
Yeah, so if you have a chip you're trying to test and it's on wafer and you have to go through all these probes and all those discontinuities, the standalone equipment like a signal source or a spectrum analyzer is really difficult to compensate for all those losses, and you have to pre-measure everything. With the network analyzer, you put an open short load chip in the fixture and it characterizes that. So then we can apply that fixture characterization to all the other measurements. If you're doing demodulation and you've got to remove the effects of frequency response, we can remove all those effects without having to pre-measure stuff, because it's all done as part of the normal calibration.
So when you say pre-measure stuff, what does that actually mean?
Basically, they would take the cable that goes from the spectrum analyzer to the wafer prober, and they'd have to measure that on a network analyzer. Then they'd have to take the probe and measure
Oh.
the loss from the probe to the probe tip. Then have to combine those in an Excel file, then download that offset into the spectrum analyzer to know the right power at the right place.
Oh, interesting.
So it could take you a couple of days to do that.
Yeah, yeah, yeah. Yeah, so like if you had a signal generator that was just sweeping from like 0 to 10 gigahertz, you're saying some cable might put in some unknown impact at like 5 to 6 gigahertz, and you'd have to characterize that, and you're saying you'd have to then adjust for that somewhere else.
Right. And with older systems, they would literally have to program a single frequency and then adjust the power level up or down according to that loss of the cable. Maybe your
Wow.
cable goes through a switch matrix, and then the switch matrix goes to
Yeah.
an on wafer probe. And someplace in there it's not great. So it has a little narrow band dip of 3 dB. So half the power is gone. And so you have to point by point kick up and down the power as you're moving across. And that might slow you down 1,000 times slower than if you had that integrated into your system.
Yeah. I would imagine that at some point too you'd start to be able to reduce the cabling needs. Not that you would go with bad cables or bad test heads or, test probes or whatever, but I'd imagine that you'd be able to not be as rigorous as otherwise needed, because if you're adjusting for everything and it's like provable that you can adjust for it, then no big deal, or less of a deal.
That's pretty insightful. That's one of the things that we can do. So we're getting into making modulated measurements, and it's really hard to do a clean job of making a source pristine if you want to make some kind of what's called QAM modulation where
Mm. That's the one. Is that the one where like it's in the little tiny circles? I've seen that on
yes,
the Siglent spectrum analyzer had that. I had no idea what I was looking at, but it looks so cool.
16 little dots, and you want them to be tiny little dots, and it's really hard to make them tiny little dots.
Yeah, I
And
bet.
our signal source guys work on that and struggle with that to make that perfect. And then you pass it through a cable, and it's no longer tiny little dots anymore.
Right, right. It looks like a pepperoni pizza at that point, then, huh?
Right. And what we can do with a network analyzer, we do this today. I'm actually going to be presenting some of this at a webinar a little later in the
Mm.
month. We can capture that response with the network analyzer because we have a way to calibrate it. And then we can go back to the source and feed it a distortion correction signal and make it look perfect. So we can
Mm.
essentially make your source look perfect at the interface of your device a meter away from your signal generator.
Wow. Yeah, that's really cool.
That is what's driving people to these multifunction tests. Is sometimes in the real world manufacturing, they can't connect directly to their signal generator, so they
Mm.
have to go through a switch matrix for all the testing, and they got to go through the thermal chucks because they got to test it hot and cold, and all that for the new 5G stuff. Without these corrections, they practically can't make the measurements.
Yeah. I'm just imagining like bending, like, so if you had like a test head that had like 100 pogo pins on it, and then Bob is careless one day and he bends one of the pogo pins, and it's like, oh, we have to remove this entire test head and recharacterize everything. It's like, Bob, you're fired.
Yeah, so yeah, I was just involved with a situation where almost like that. We said we've got this
Uh-huh.
data, we can see this got this one bad transmission line. Is there any way?
uh
It took us weeks to get the data. Is there any way we can figure out what that effect was? And there is actually a way that we can look at the data and say, okay, this effect is caused by this bad spot, and we can figure out what that bad spot was and then regenerate all the data again as though it wasn't a bad spot.
oh. Huh.
Call that automatic fixture removal. And we charge people a lot of money for that. We don't give that
Uh-huh.
one away. And
Yeah,
it's
yeah.
been super popular because with that, you can basically just take your probe or the end of your coax and just leave it open, and we'll figure out all the badness of the coax cable and then connect it to your device. You don't even need to calc it anymore. That's also in the second edition, explains how we do that.
Okay, that's great. Yeah, I mean, like, do you ever worry that, like, I mean, this seems like software kind of just smoothing out the edges and things like that. Do you ever worry that it's not capturing reality? I mean, like, I know that you guys prove it, but like from like just a gut feel kind of thing of like, oh well, are we actually removing? Like, is it like provable? How do you actually tell that it's actually flat and removed and everything's copacetic?
That's a lot of actually the work I personally do is not proving that something is can measure a good thing good. You got to be able to prove that you can measure a bad thing and show that it's bad, that you haven't
Yeah.
that you don't have a ripple that's been smoothed out, that's a real ripple.
Yeah. Right.
We spend a lot of time and a lot of effort, understanding exactly where all these errors come from, which ones you can correct for, which ones you can't correct for. Then figure out ways. This is what we call a process called verification that says, I'm going to measure a thing. We measure a good thing and make sure it measures good, and we measure a bad thing and make sure that we can see the right amount of badness.
Yeah. Right. Right. Exactly. Yeah. You need to have like golden samples almost, but in this case, a bad golden sample as well. It seems like.
Exactly. You have to. Noise figure is one of those things that everyone just wants the noise figure to be low. So if you built a system that always measured everything 1 dB lower than it really was, nobody would complain in manufacturing. They'd all think
That's
that
right.
was great.
But then the FCC would give you a call, right?
Yeah, maybe the Dish TV subscriber who can't get his signal
Yeah.
when it rains. He's
Yep.
guy's really good. And that's the interesting thing about all these digital modulation schemes is they, degrade slowly. So if you have equipment that's not really
Right.
that great, instead of getting 100 megabits per second, you'll get 10 megabits per second.
Interesting. Yeah. Yeah. I mean, yeah, and that yeah, like you said, there's the degrading there. I think about these like correction codes that are in every digital transmission too, and it's just like they're digging so much out of the noise already. I don't know, it works pretty well. So, but then it's like your expectations change, and now I can go in an elevator and it's no big deal, but it's a little bit worse for my phone now than it used to be or something.
It's the difference between it goes from good to dead to, it gets a little pixelated for a little bit. If somebody jumps around the screen too fast, it's pixelated. And what's happening there is you're just seeing that's a spot where the data stream had to slow down because a car drove in front of the antenna or a giant rain cloud came across. And the radios are constantly communicating and saying, okay, you got to drop to a lower modulation rate. You got to give me more. The lower the modulation rate, the more signal to noise you have. And at these high scale modulation rates, the signal is hardly out of the noise at all.
Yeah. I mean, it's as close to magic as I can imagine.
And there's a reason why these companies like the giant one in Cupertino have tens of thousands of engineers working on this stuff because it is really complicated.
Yeah. Question about this popped up a little earlier, but I don't think I asked it. So the 8753 on my bench is a 2-port VNA.
Yes.
And there are now higher port numbers. Is that right?
Yeah, we go up to, I think the biggest we've commercially shipped is 66 ports.
Oh my gosh. So why is it higher? What are the added ports in that case?
So they're essentially you have an amplifier, it's got an input and an output. Say, okay, now I'm going to have a differential amplifier. So differential amplifier actually has 2 inputs and 2 outputs, right? It's got 4 ports to it. Yeah. And you say, okay, but now I've got an 8-channel MIMO differential amplifier. So an 8-channel times 4, that takes 32 ports. And we sell lots of 32-port systems for these 8-channel MIMO test sets. And the thing is, a normal network analyzer, you can say, well, I'm going to turn on source on port 1, and then I'll measure to port 2. And then I'll measure from 1 to 3 and 1 to 4 and 1 to 5. So you got to take a measurement for every one of those paths. And if you have a switching network to switch it around, it's a measurement per path. So I don't remember the number, something like, it's exactly n times n minus 1 over 2. So it's, if you got 6 ports, it's 6 times 5 over 2. It's 15 measurements you have to make. If you have 32 ports, it's whatever that is, 32 times 15 measurements that you have to make. Those hundreds of measurements get really slow. But if you have a 60-port analyzer, you turn on port 1 and you measure it on all other 60 ports at the same time. So you really drop the throughput time. And these manufacturers, they cannot take 10 minutes to test an antenna that they're going to put on a car. They have to test it in a second. So the more ports, it just means making more measurements at the same time.
Okay.
It's just exactly the same as a multi-core processor.
Got it. Yeah. Yeah. I mean, I think I think I've seen up to maybe 8 for the bench. You know, I browse through these catalogs, and my jaw is usually on the floor in terms of. I'm like, oh, is my consulting company going to pay for that this month? No, it is not. But maybe I'll rent one sometime. And I have seen up to 8, and it does seem like that would make sense then on the bench with the differential, or I guess 4 in that case would be a differential amplifier, that sort of thing.
12 ports is really popular. We make so in this the handheld USB network
Mm-hmm.
analyzer, we make a 6-port version. So you take
Mm-hmm.
two, and the reason 12 ports is popular is if you have differential pairs, you have the signal pair, the adjacent pair, and the alternate pair, and they want to know how much signal is cross-talking from one to the other. So you got 6 connections on one end and 6 connections on the other end, and
Mm.
that's a real popular configuration. And that's also why the PXI analyzers have become so popular because you
Oh,
can,
sure. Yeah.
configure up a 4-port system, and then your buddy on the aisle away, he has a 4-port system, and when he goes on vacation, you can steal 2 of his modules and make your system an 8-port system.
Right, right. Hey, Bob, you're taking a day off today because, well, I need to do more measurements.
It exactly happens that way.
Yeah, yeah. Hmm. That's great. That's great. So, back to the book real quick. So, people get the book. What do you think they should be starting with? Is it just kind of a sit down and read it kind of thing? Is it a sit down and read it before you buy a VNA type of thing, or is it you already have a VNA, you've already read other books, and you're getting deeper?
If you gotta, so it's really written around the modern VNAs. So 87, the first 3 chapters are all about kind of the older VNAs. It's the theory, the kind of underlying theory. And if you always wonder, how does this error correction thing work? It explains that. But the
Mm-hmm.
later chapters, it's really written as a handbook. So you say, right, I got a low noise amplifier I have to test, and it's got 60 dB a gain, and I'm getting terrible results. Let me take a look in the chapter on
Mm.
amplifier test or noise figure test. And there'll be 20 pages there that you'll have to read through, and then afterwards you'll understand, oh, this is all the things that I was seeing that was
Got
causing
it.
me trouble. So it's really designed to be a handbook where you got a particular problem, you need to test a frequency converter. Go look up the best way to test a frequency converter.
That's great. Yeah. Yeah. Between this book and Tom Lee's book on microwave chips, which after the first couple chapters, Tom's also been on the show. And after the first couple chapters, I'm like, silicon RF stuff. I'm not, that's not me.
Yeah.
But yeah, the first chapters are very, very, very helpful for those sort of things.
Yeah. And so in the book, I basically say, here's the 6 steps you need to do to test anything and with a network analyzer. And people always, when I ask the question, I go to seminar, I say, okay, what's the first thing you do? Everybody says calibrate. And no, that's quite a ways in the process. The first thing you do is you connect, and this has been true for the last 30 years. The analyzers are all pre-calibrated at the factory, so they're pretty good.
Mm-hmm. Yep.
So connect your thing up, make your measurement, take a look. Does it make sense? No, my gain's minus 30 dB on my amplifier, and my isolation's
Mm.
plus 30. I hooked it up backwards. So let me turn it around. So first thing you do is you make all your measurements that you want to make without doing any calibration. Then you adjust your cables, your connectors, your adapters,
uh,
wiggle your part to make sure it's stable. So I say first is connect it, measure it, then optimize your measurement. When you got
mm,
everything working pretty good, then take the time to calibrate.
mm. Yeah. So I'm almost like fixturizing on your bench. That's another thing that I've learned is just like tape things down.
Oh,
Like,
yeah, that helps, especially if you have bad cables.
yeah, which I do mostly. Yeah.
Taping your cables down is just like keeping your dog in a penned in
Yeah.
area.
Yeah.
Can't
Yeah.
get into trouble if it doesn't move around too much.
That's right. Yeah. I think that one of the big problems for me was that I was at a shared workspace when I got my VNA, and I had to clean up every night. And so every day I had to go and pull this thing out and like redo measurements and redo my fixture. And it's just like, oh, this is just not, it's not as mobile as I wished it would have been.
So network analyzers like to be turned on and then you turn them off when you retire.
Right. They've got that stable temperature operation, and they're all warmed up.
Yep, and they just like to sit there and be warm and stable, and there's a lot of
Hmm.
metal in there, so you don't want it to move around.
Right.
It's all physics, right? It's the speed of light. The cables
Yeah.
inside, as they get hot and cold, they stretch and shrink, and that moves your phase around, and that's what causes you trouble.
Yeah. It's almost like the devil kind of thing. It's like, okay, yeah, maybe your cable's hot and it's, putting something into the measurement, well, it's not that bad, but it's, you know, if it's having some impact on your measurement tool or your measurement path, and it's like, but you know it, and it's there, and it's the same, and it's like you don't need to, you just calibrate it, it's gone, you know. Like
Calibrate it, it's
that's
gone, and everything
yeah.
will be good.
Yeah, I think that's another thing that's interesting about this kind of area is that it's not there's not really any absolutes. That's another thing that was different for me coming from the DC side of things. You know, there was like a measurement standard is tracked all the way back to some NIST lab, some fancy resistor or current source or something based on a SI unit, and I it's very different here.
Well, we are based on impedance, and that goes back to
Mhm.
the diameter of an inner conductor relative to the diameter of an outer conductor on a magic airline that's been measured to the so
Oh,
impedance,
really? Oh, okay.
the reference of impedance is distance. And they have an airline at NIST that they measure, and they say, yeah, this airline is this impedance, and then they use that to calibrate a system that then you use to calibrate your loads and resistors and
Oh,
capacitors.
okay. So that is tracked all the way back. The I
Yeah,
guess, yeah, and
yeah.
I guess there's factory calibration I could do. I just meant like the relative once it's in hand. I don't even know when mine's been calibrated last, so who knows how good mine is. But
So there's two kinds of calibrations, and in my book, I'm a little bit more careful than I am in just language. When we talk about calibration from an instrument side, what we're saying is we've measured the instrument and we verified that it meets all the published specifications. And that's what that cal sticker says. It says it meets its specifications. The kind of open short load calibration, that's what I really call error correction. And that's the thing that most people deal with is the error correction. And okay, dirty
got
little
it.
secret here. You can be pretty far out of cal and on an instrument and still have error correction return it to a reasonable measurement.
Oh, I think mine that's been the eBay buy and shipped to me and has a 2-year-old certificate. I think mine is pretty far out of calibration probably.
But a good error correction will probably make your measurements look pretty good unless it gets so far out that the there's only so much you can correct before the numbers start to fall apart.
Got it. Got it. So I shouldn't title this episode Joel Dunsmore does not endorse calibration or something like that. That would probably be not correct.
That would be not correct and not
Yeah.
good.
Yeah. Right.
Now, calibration is how you know that your instrument works the way it's supposed to work, and the error
Uh
correction
huh.
is how you make it perfect.
Yeah. Yeah. And especially the test setup thing too. Again, like Jeff, friend of the show and friend of me, Jeff, he helped me through a lot of this stuff. And I didn't quite understand the test setup kind of piece. And that really seems like a lot of the error correction stuff. The absolute measurement against NIST standards is interesting too, because it comes from somewhere, it's got to start somewhere.
If you have one of our cal kits are characterized against a NIST artifact.
Ah,
So
got it. Yep. And that's why yeah, cal kits are not cheap.
they are not cheap. Or you could
Yeah.
put a 50 ohm resistor on a PC board and call that a cal kit. I talk about that in my book as well on
Yeah.
making your own
Great.
calibration standards. And if you can do that and it's stable and you characterize it against a good calibration kit, you're going to get good results with it.
Yep. Yep. Yeah, and I think it comes down to like what you need in your own system, in your own reliability of, if you're making something that's going into a cell tower, it's probably a lot different than something that you're making for, a hobby project or something similar.
Or if you're making something that's going to fly to Mars and you want to make sure that the signal
Yeah,
lines
right.
up. So the
Yep.
aerospace defense guys, people making satellites and making radars, they're like at the top tier of everything has to be in calibrated. You have to run your daily calibrations. You have to record any variation
Oh
because
wow.
that stuff has to be perfect. Satellite stuff has to be perfect or you're going to end up with dead junk in space. Cell towers have to be pretty good, but if they're not perfect, okay, maybe you can't connect to 100 cars, you can only connect to 20 cars. Handsets, they're maybe a little less perfect. And ham radio guy tuning up his 80 meter antenna, well, as good as it needs to be.
Right. Right. Yeah. As far as he wants to get on a contest day, I'm guessing, right? I mean, some of
Exactly.
them are getting very, very far. It's very impressive sometimes. That's great. Joel, we are doing a giveaway for the book, I believe,
Oh,
right?
I think we are. Shamri was one of our colleagues
Yes.
here is going to arrange that with you.
Yes. So we will have a form down below. If people are interested, they can put into the form their information, which we never sell or use for anything else other than drawing a name for sending out books. But we'll be doing that as a thank you. Well, first off, thank you for being here, Joel, and thank you for sharing some of this knowledge, both here and in the books that we'll be giving away. So it's been great talking to you.
Great. I bet. By the way, I've really enjoyed. So I found you and started binging your show, and
Great.
have enjoyed it very much. I always enjoy when Dave talks about RF. It's good for a chuckle.
Got it. Yeah. That's it's fun to have one topic that I know a little bit more than Dave about. It's.
But if you have any more questions on your network analyzer, feel free to give me a buzz.
I have to say that is a great honor to be able to talk to someone like you, and the person that designed the box that's actually sitting on my shelf is that's pretty darn cool. That's pretty darn cool. So thanks again, Joel.
Well, hopefully it'll keep working, and thanks for having me on.
Yeah, thanks so much. We'll talk to you soon.
All right, bye-bye.
Don't forget to fill out our annual listener survey to be entered for a chance to win one of 3 copies of Joel's book. We always love the feedback our audience has. If you'd like to give direct feedback and support, join the crowd and the Discord channel at patreon.com/theamphour.